Video lecture 19D, the Nernst equation. So far, we've looked at only standard galvanic cells, where the solution concentrations are about 1 molar. However, if we want to look at non-standard galvanic cells, where the solution concentrations are not 1 molar, or where the partial pressures of our gas phase species are not 1 atmosphere, we need to use a different equation to calculate the cell potential. We can use the relationship between delta G and E cell to come up with an equation that relates a non-standard cell potential to the standard cell potential. This equation is now referred to as the Nernst equation. In this equation, the non-standard cell potential is equal to the cell potential minus RT over NF times the natural log of Q, where F is Faraday's constant, 9.65 times 10 to the 4th coulombs per moles of electrons. R is the thermodynamic gas constant, 8.314 joules per mole times Kelvin, and N is the number of moles transferred in the cell reaction. As before, we can combine the constants R and F and use a standard temperature of 25 degrees Celsius, as well as converting the natural log of Q to the common log of Q to get a simpler equation that E cell is equal to standard E cell minus 0.0592 volts over N times the log of Q. This equation can be used to calculate a cell potential in which the conditions are not standard. This requires us to calculate a reaction quotient first. Note that in this equation, the reaction quotient is referred to as a thermodynamic reaction quotient. And for cells of mixed phases, that is, they involve gases and aqueous solutions, we are free to substitute in partial pressures in atmospheres and concentrations in terms of molarity. Here's an example. We are going to calculate the cell potential of our copper-zinc cell when the concentration of copper 2 plus is 0.01 molar and the concentration of zinc 2 plus is 0.1 molar. If you recall, the overall cell reaction for the copper-zinc cell is given below. Zinc in this reaction is oxidized into zinc 2 plus, and copper 2 plus is reduced to copper solid in the cathode. If you also refer back to the figure, you'll notice that the voltmeter reads 1.10 volts. This is the standard cell potential, assuming that the solution concentrations are 1 molar. We also know that for this reaction, a total of 2 moles of electrons are transferred. Zinc loses 2 electrons as it's oxidized, and copper gains those 2 electrons as it's reduced. We are now ready to calculate the reaction quotient. The reaction quotient will equal the ratio between the zinc 2 plus concentration and the copper 2 plus concentration. If we plug in the given concentrations, we get that Q is equal to 10. We are now ready to substitute this all into our Nernst equation. We substitute our standard E cell as 1.10 volts, moles of electrons transferred as 2, and Q equal to 10. This gives us a final cell voltage of 1.07 volts. This means that under these conditions, the cell potential is lower than it is for the standard cell. Note that if the second half of the equation equals the cell potential, equals the standard cell potential, then the entire cell potential would equal 0. This explains how batteries die. the concentration of the battery's contents change such that the standard cell potential equals 0.0592 volts over 2 times the log of Q. This will then give you a zero cell potential, or dead battery. The Nernst equation has several interesting applications. First of all, you could actually make a galvanic cell using the same half reactions, as long as you do not use similar concentrations. This is referred to as a concentration cell. The concentration cell pictured uses the copper 2 plus half reactions. However, the cathode has a higher concentration than the anode. This is crucial in order to have a cell with a positive voltage. The free energy difference that allows for the cell to work is because of the two different concentrations, and this will give you a non-zero E cell. The half cell with the lower concentration will act as the anode. So in this case, the 0.01 molar copper sulfate electrolyte solution, along with the copper electrode on the left, will act as the anode since the concentration is lower. Therefore, the half cell with the higher concentration will act as the cathode. In this case, the 2 molar copper sulfate solution on the right serves as the cathode, and copper will undergo reduction there. And electrons will flow between the anode and the cathode until the concentrations equalize. This means that the system will reach equilibrium and the cell potential will equal 0. Let's calculate the cell potential of this concentration cell. Here's our overall reaction. Everything on the left-hand and right-hand sides of the equation look the same, and you might think there's no net reaction. To keep things straight, let's write our concentrations underneath the appropriate species. The copper 2 plus on the left-hand side of the equation comes from the cathode half reaction. This is the 2 molar solution. The copper 2 plus on the right-hand side of the equation comes from the anode half reaction, which is 0.01 molar. Since the two half cells are the same, the standard cell potential will be 0. However, 2 moles of electrons will be transferred between the two species. We need to calculate Q to get the cell potential. In this case, Q is equal to the concentration of copper on the anode divided by the concentration of copper for the cathode. This gives us a Q that's equal to 0.0050 for a reaction. We are now ready to plug in our values. We end up getting a cell potential of 0.068 volts, a non-zero cell potential. You might wonder, what will we use a concentration cell for, since no real chemistry is happening? Actually, concentration cells have a very real application related to what we've done in this course. This is the basis behind making a pH electrode. pH electrodes you can consider as a special type of concentration cell. The simplest brute force way to make a simple pH sensor is to combine 2 hydrogen half cells together. One half cell would be the standard hydrogen electrode, where you have a 1 molar concentration of HCl. The other half cell would be your test half cell. That is, it would contain a acidic or basic solution where you do not know the H3O plus concentration. In this example, our test cell is acting as the anode, and the standard hydrogen electrode is acting as the cathode. We can determine what the pH will be using the Nernst equation. First of all, let's write an overall reaction for our hydrogen concentration cell. Notice that this reaction has both gases and aqueous solutions. You will need to consider the concentration of the solutions as well as the partial pressures of the hydrogen gas. All of these values can be inserted into the Nernst equation. To keep things straight, let's remember that the H plus that appears on the left-hand side of the reaction comes from our cathode and has a 1 molar concentration. The H plus on the right-hand side of the equation comes from our anode, and we do not know the concentration of this. This will be determined using our pH measurement. Remember that since this is a concentration cell, the standard cell potential will equal 0 volts. And also 2 moles of electrons are transferred. We are now ready to plug things into the Nernst equation. Notice that our Q contains all 4 species participating in the reaction. The anode materials are part of the numerator of the reaction quotient and contains both the test solution concentration and 1 atmosphere for the partial pressure of the hydrogen. Similarly, on the bottom, the cathode materials contain the 1 molar solution of H plus and 1 atmosphere partial pressure of hydrogen. All of the ones will cancel each other out, and you'll just be left with the concentration of the test hydrogen plus solution. We can use one very useful property of logarithms, that is that the log of x raised to the y power is equal to y times the log of x. This brings the 2 outside of the logarithm term and cancels it out with the 2 in the denominator of the fraction. This gives us that E cell is equal to 0.0592 volts times the negative log of the H plus test solution concentration. Remember that the negative log of the H plus concentration is the pH. Therefore, the E cell is directly related to the pH of the solution. You would measure the cell potential and then convert it into a pH using this equation. This cell could be used to calculate pH. However, it's dangerous to operate due to the hydrogen gas and not as portable. So modernly, we use a pH glass electrode. These contain half-reaction couples that do not involve gases, but gives an overall standard cell potential of 0, allowing us to calculate the pH of a solution. The glass electrode pictured to the right is a silver-silver chloride electrode, which is often used as a test electrode for measuring the concentration, the pH of a solution.